here is another example. We have to find the Hilbert transform of a function f, where my function is defined as t divided by t square plus a square, where a is positive. Okay, so the Hilbert transform of the function is defined as, again, this Cauchy principal value from minus infinity to infinity, and we use this function t by t square plus a square times 1 by t minus x dt. Now, we are integrating with respect to t now. So, to evaluate this particular integral, I am going to break down this ratio of two rational functions, this product of two rational functions using partial fractions as follows. So, I can see that this particular integral is 1 by pi, the Cauchy principal value integral of 1 by a square plus x square. So, I can take this factor out, and this is times a square plus t square plus x divided by t minus x minus x t divided by t square plus a square. Now, all students can check that the simplification of these three factors times this factor is going to give me back this integrand inside this integral here. Okay, so, why I did that? Now, we can see that this first factor is independent of t. So, this can be treated as a constant and pulled out of the integral. The first term in this second bracket is purely a function of t. So, I can integrate it out, and that will give me a tan inverse, and the third one is nothing but the integral of 1 by t minus x, that was done here in example 1, and the fourth one is going to be 0 because this integral is an odd function of t. So, from negative infinity to infinity, this fourth term, the integration of this fourth term is going to give me 0. So, let us recap what I just said. So, what I said was, let me rewrite this expression. I get my integration as follows. This is integral from negative infinity to infinity a square dt divided by a square plus t square plus x times integral infinity to infinity dt divided by t minus x minus integral negative infinity to infinity negative x times t dt divided by t square plus x square. Okay. We see that, as I said, this integral is going to give me a tan inverse a times tan inverse of tan inverse of t by a, and the second one is going to, the integration will give me right away x times log of log of, let us say I write down the answer, log of r minus x by r plus x. Well, this is an infinite integral. So, I can always take a limit r tending to infinity of this integral. See this particular integral was already evaluated in our example 1. So, I am just using that result to integrate it from minus r to r and take the limit r tending to infinity. So, again that is going to give me 0, and the third one is going to be 0 because this is an integral odd with respect to the variable t. The third one is an integral which is an odd integral with respect to t. So, when we integrate over a symmetric domain, it is going to cancel out. Okay, so, what we get is the following. I get 0 from the second integral and the third integral. The first integral, when I evaluate, I get this equal to 1 by pi 1 by a square plus x square times a tan inverse t by a from, well, when I plug in negative infinity to infinity, I get pi by 2 each time, and let me just simplify to give you the answer. So, I get 1 by pi a square plus x square times a pi. So, I can cancel out this pi to come up with the final answer to this problem. Okay. So, moving on, let us now look at another example. So, I need to find the Hilbert transform of a function where my function is given by f of t equal to cos omega t. Okay, so, then let us look at the transform. This is given by 1 by pi integral from negative infinity to infinity cos omega t divided by t minus x dt. Okay, so, we see that this is also equal to 1 by pi. I am going to rewrite this integral, the integrand, as follows: 1 by pi negative infinity to infinity cos omega t minus x plus omega x divided by t minus x dt. Okay. So, then the reason to do this change is because of the following. I am going to break down this numerator into two terms in using my sum rule, into two integrals using my sum rule, and then use a change of variables to evaluate the first and the second integration respectively. So, let me use the sum rule for cos of two angles to get the following expression. So, this will be equal to integral. So, these are all Cauchy principal value integrals from negative infinity to infinity cos omega t minus x cos omega x minus sin omega t minus x sin omega x divided by t minus x times integral dt. Okay. So, let me just say that this is the following integration here. So, now I am going to break this integral into two parts. We see that, so let me just break this down. This will be cos, integration variable is the t. So, I can take out cos omega x out of the integral. This will be, the first integral is follows: cos of omega t minus x divided by t minus x. Well, let me write this down in the next page to give you a better picture. So, what I get is the following. The expression looks like the following. This will be cos omega x divided by pi, the principal value integral of cos omega t minus x divided by t minus x times, well, dt times, well, the second integral will have a minus sin omega x by pi integral sin omega t minus x divided by t minus x dt from negative infinity to infinity. So, then we see that this is also equal to, we see that the first integral, when we have to evaluate, this will be in both these integrals we see that the variable t minus x is appearing. So, let me use a change of variables. So, I change my variable t minus x to the variable t, let us say another dummy variable here. So, we see that when t minus x goes from negative infinity to infinity, my new variable also has the same limit. So, then my integration looks as follows. So, this becomes from negative infinity to infinity cos omega t by t. Well, so dt is going to give me the same element d capital T minus sin omega x divided by pi integral from negative infinity to infinity sin omega t by t dt. Okay. So, next we see that this first integral is an odd integral. The term on the numerator is even, the term in the denominator is odd. So, for an odd integral I get a 0. Okay. For this particular integral, the value is known from standard calculus textbooks. So, I am going to right away evaluate the value of this integral to give you the answer, and it is equal to pi. Okay. So, please refer to standard calculus to see that the value of this infinite integral is pi. So, I get that my answer is, well, the first integral is 0, the second integral gives me a pi, and I get my answer to be negative cos omega sin omega x. And as I said, so we see that, so the conclusion of this example is that we began to find the Hilbert transform of f hat h of cos omega t, and we saw that this is negative sin omega x, or this is also equal to cos omega x minus pi by 2. And what I want to highlight here is that the Hilbert transform does a phase shift of an angle of 90 degrees on the Fourier variable, the Fourier transform variable. Okay. So, then I have lots of properties of Hilbert transforms, which I want to write it down one by one, and I am going to prove some of those results. Okay. So, some of the basic properties of my Hilbert transform are as follows. So, I have that the Hilbert transform, so I denote my Hilbert transform as this simple h. So, this is to be distinguished from the Hankel transform, where I use a curly h. So, this is a simple h. So, Hilbert transform of the function at evaluated at t plus a is the Hilbert transform. So, either I use this capital H or I use this hat with a subscript h, these mean the same thing. So, Hilbert transform of the function evaluated at argument t plus a is f hat h of x plus a. Okay. Then the next property, we see that this is the shifting property here. Then we have the so called scaling property of the Hilbert transform. So, h of f of a t is equal to f hat h of a x. Then we see that Hilbert transform of f of negative a t is negative Hilbert transform of negative a x. Okay. So, let me just write down all these properties, and I am going to prove some of the more tricky ones. So, all these things are quite straightforward to see using the definition of Hilbert transform. So, then there is a fourth property which tells Hilbert transform of the derivative of the function is the derivative of the Hilbert transform. The sixth property shows that the Hilbert transform of t times f t is equal to x times the Hilbert transform of f plus 1 by pi times integral negative infinity to infinity f of t dt. So, as people can see that this particular property can be right away shown using integration by parts. So, use the definition of Hilbert transform and integrate by parts to arrive at this result. The seventh property shows that the norm of the Hilbert transform, is also equal to the norm of the function, where I define my norm of the function by a so called inner product in the L2 sense. So, it denotes an inner product in the square integrable function sense. So, square integrable over R. Okay. So, then another property shows that the Hilbert transform of the function, let us again I denote it by f hat h, is, well, if f hat h is the Hilbert transform of the function, then the Hilbert transform of f hat h is negative f. We have seen this from the property of the inverse transform, inverse Hilbert transform, that we get a minus sign when we take the Hilbert of a Hilbert transform of f. Finally, another property shows that the inner product, again in the L2 sense, the inner product of f with h g is the inner product of h f with g, and let me write down another one in the same fashion. The Hilbert transform of, sorry, the inner product of the Hilbert transform of f, so these are all Hilbert transforms applied on the function, with g is equal to the Hilbert transform of f with negative h g. Okay, I am going to denote these inner products results by the Parseval's formulas. So, these are the Parseval formulas for in relation to the Hilbert transform. Okay. So, I am going to show you some results here. So, out of all these 9 results, let me show you the proof of the first one, and the proof of the second, third follows in a similar fashion as first. I am going to show you the proof of the fourth one, and I am going to use, well, I can also show right now, I can show the proof of the seventh one, and also let us say, well, the eighth one I have already shown, and I can show the ninth one as well right away. For the others, I leave it as exercise. So, students should definitely try this at home to derive all these properties. So, let me show you some of the selected ones, how we get to the result. So, the first property shows that the Hilbert transform of f of t plus a is the Hilbert transform at evaluated at x plus a. So, notice that the left hand side is given by the Cauchy principal value integral of 1 by pi dt times, well, f of t plus a dt divided by t minus x. Okay, so, what we see is that this is 1 by pi integral, the Cauchy integral of f of u, where I have defined my variable u to be t plus a. So, I substitute instead of t plus a, I substitute u, or I substitute instead of t, I substitute u minus a, and also that du is equal to dt. So, then I get that this is f u du, and then in the denominator I get that I have this expression u minus a minus x, or let me write it in the following fashion, and I see that this is nothing but the Hilbert transform of the function evaluated at x plus a plus x, which is what my right hand side is. Okay, so then let us look at the fourth case which I wanted to show. So, I have to show that the Hilbert transform of the derivative is the derivative of the transform function. Okay, so then the left hand side is given, again it is going to be given by this following Cauchy principal value integral, which is integral f prime t dt divided by t minus x. Now, I am going to use integration by parts, integration by parts. So, in particular I am going to use this as my first function and this as my second function to do the integration by parts to arrive at. So, first function integral of second, first function integral of second, and let me take the 1 by pi out. So, I put the limit from minus infinity to infinity. Again this is this, well I see that let me keep this value as it is and I am going to evaluate it right away. And then the second half of the integration by parts is negative 1 by pi integral the Cauchy principal value integral f of t and derivative of the first function, which is t minus x square, that will give me a minus sign. So, that becomes a plus dt. Okay. So, then notice that the first term I can safely take it to be 0. So, the first term will turn out to be 0 provided my function f is bounded, right. So, if the function f is bounded, then when I evaluate this term at these limiting cases, my denominator blows up and for a bounded function this value is 0. The second case, we see that the second part of the integral is nothing but the derivative of the same Cauchy principal value integral of f of t minus x dt. So, if we were to differentiate this integral with respect to x, I am going to get this following integral here, and so that gives me the right hand side that we were hoping to find. Okay. So, then